So I want you to think about empirical formulas. Okay, so the definition tells us that it's the smallest whole number ratio of elements in a chemical compound. So let's look at water here. Okay, if I put up the chemical formula for water, what's the ratio of hydrogen atoms to oxygen atoms? 2 to 1 is the ratio, okay? What about this ratio? Oh, yeah, you can't really see it, sorry. So what's the hydrogen to oxygen ratio here? 1 to 1/2 or 2 to 1, right? It's still 2 to 1. But does this work? No, that's right. We can't have half of an oxygen atom. We can't have subscripts that are not whole numbers. Okay, we talked about that in the conservation of, conservation of mass section. We have to have whole number ratios. So this doesn't work. What if I have, okay, here's water. What if I have H4O2 or H6O3? Yeah, it's still 2 to 1. However, these two molecules are not water. Okay, they're not water. Just because they have the same ratio as water does not mean that they are the same compound. Okay, they have a different structure, they have a different shape, they have a different molecular makeup. Just because the ratio is the same does not mean that they are the same compound. Okay, so that's important for you to understand. That just because it's 2 hydrogens to 1 oxygen does not mean that all of these compounds are water. Okay, so this right here, H2O, is the empirical formula of hydrogen and oxygen. Okay, hydrogen and oxygen bonded together, that's the empirical formula. That's how it works. Okay, so this compound might have the same ratio, might use the same elements, but it's not the same compound. So what we're going to do is determine how to build these empirical formulas. Okay, and we're going to do that working backwards from percent composition that we learned how to do last class. Okay, we learned how to determine how much of each compound was made up of a specific element. Now we're going to learn how to take that percent of an element and build it into a compound. All right? Okay. We're going to do the example on page 245 if you want to follow along in your book. We're going to do it up on the board so you can just watch up there if you want. So, learning about percent composition, we determine if a compound was made up of this much percent of oxygen and this percent hydrogen. That was called percent composition. So now we're going to work backwards. And what's given to us here is that a compound is made up of 78.1% boron and 21.9% hydrogen. Okay, they've taken this sample of some substance and they've somehow determined that 78.1% of it is boron and 21.9% of it is hydrogen. Okay, so they've done that for you. Now we want to determine what actual substance this is or what empirical formula this is. So the first step that you do here is you take your percentages and you just turn them into grams. So we take this and we say we have 78.1 grams of boron and we have 21.9 grams of hydrogen. Okay, so instead of working with a percent, we act like we're working with 100 grams of the substance. So therefore 78.1 grams of it would be made up of boron and 21.9 grams would be of hydrogen. Yeah.
Is it always going to add up to 100?
Because these percents should always add up to 100.
Okay.
Yep. So whenever we're given a percent of an element, then we always just put that right into grams. Okay? From there, we take each of our grams and we convert them to moles. Okay, so do these separately. You convert grams of boron to moles of boron, and you convert grams of hydrogen to moles of hydrogen. So let's go ahead and do that. 78.1 grams of boron. I make my T-chart. I want to go grams of boron on the bottom since that's what I want to get rid of. Moles of boron goes on top. If I'm going between grams and moles, what does moles get? A 1. Yep. the 1 and tell me how many grams is in 1 mole of boron. 10.8. Okay. So yeah, you need your periodic table out if you don't have that already. So if we want to solve for moles of boron, we multiply across the whole top, divide by the whole bottom. All right, Brent, what'd you get? Okay. Or Keaton, what'd you get? I'm just kidding. All right, 7.23 moles. Okay, that's moles of boron. You guys can do these grams to mole conversions, no problem, right? You should be able to do these in your sleep. All right, so tell me what the number of moles of boron we had again. 7 point what? 23. Okay. Now we still need to calculate moles of hydrogen. So we have 21.9 grams of hydrogen, and we need to go to moles. So how many grams is in 1 mole of hydrogen? 1. Okay, so that means we have 21.9 moles also of hydrogen. Okay, so thus far to get to this point, we've converted our percents to grams just by switching the units. We've converted our grams to moles. Now to start looking at our ratios, we're going to take the smallest number of moles that we have. So which one of these is smaller? 7.23 is smaller. We're going to take both of our mole values and we're going to divide them by our smallest number of moles. Okay, so we need to take 7.23 divided by 7.23, and we get 1 for boron. We're going to take 21.9 divided by 7.23, and we get 3.03. Okay, so this is essentially 3, right? We're close enough to 3 here that we can just round to a whole number. So then our ratio becomes boron 1, hydrogen 3. So our empirical formula then is BH3. Let's try one that says we're given 32.38% of sodium. We're given 22.65% sulfur and 44.99% oxygen. Okay, so this time we have 3 substances instead of just 2. We still have to build a formula out of these 3 substances. Yep, the process stays exactly the same. So our first step is then converting these percentage to grams. So you just switch them. Yeah, 44.99. This is example on page 246 if you want to follow along. Okay, so now we take these and move them to grams. We get 32.38 grams of sodium, 22.65 grams of sulfur, and 44.99 grams of oxygen. Okay, so now you need to do the mole conversions for these. Okay, I want each of you to do all 3 of these mole conversions. Should be no problem. For moles? Probably, let's go to the hundredths place for moles. Just because these have to be kind of exact. For which one?
Sodium.
0.14?
No, 1.41.
Oh, I'm sorry. 1.41. 1.41. Is that what everybody got?
Yeah.
Okay. Monica, do you have one for sulfur? Okay. Alicia, do you have one for sulfur? 0.71. Good. Okay, and Brittany, what'd you get for oxygen?
I got 2.8.
2.8.
1.
Is that what we said? 2.81? Okay. So now that we have all three of our mole values, what's our step? Divide by the smallest. Okay, so which of these three is the smallest? 0.7, or for sulfur. So we take this, divide by 0.71. We take all of them, divided by 0.71. You should always then theoretically get one of these that's just a 1 ratio, right? 0.7 divided by 0.7 is just 1 for sulfur. This should be about 2 for sodium. And this should be about 4 for oxygen. Okay, is that what we got? Okay, so now we go about building our compound. What do you think the compound's going to look like? Yeah, Na2SO4. Did you guys guess that just because those are the order that they went in? Okay, so they won't necessarily always be given in the order that you should be writing them in. Okay, but here's a little trick. They typically go in order from left to right on the periodic table. So sodium is the cation, so it has to go first. Oxygen typically goes last, so sulfur sits in between. Okay, so the cation usually goes first. Sodium's the +1. Oxygen typically will go last, so sodium fits in, or the sulfur fits in between. Okay?
You said it goes from left to right.
Yep, typically it goes from left to right, because the cations are on the left. Positives are on the left. Okay. Let's say now that you are given a 10.150 gram sample of some substance. So you have a total 10.15 gram sample. And you know that 4.433 grams of it is phosphorus. Okay? This sample you know is made only of phosphorus and oxygen. So how do we determine how many grams of oxygen there is?
Take 10.
10 and subtract 4.
Yep, 10 and subtract it out. So subtract out 4 and tell me what our grams of oxygen should be.
5.717.
Okay. So now we have our grams of each of them. Okay, so we just pretty much skipped our first step here of switching percents to grams because we are already in grams. Okay, so now we don't need to worry about percents. We're done with that. So now we have grams and we need to convert them to moles. Okay, so I want you to go ahead and convert them to moles and then we'll get moving here. Okay, 0.143 moles of phosphorus. Catriona, do you have the moles of oxygen? 357. Okay, so we have our two substances. We have our number of moles of each substance. Now we need to divide by the smallest number of moles. Okay, so that smallest number is good, 0.143. So we take one of them, divide by 0.143. We take the other one. So we get 1 phosphorus to about what?
So 3 oxygen.
About 2.5.
Okay, so it's 2.5 oxygen. So if we write out our empirical formula, it would look like this. PO 2.5. Does that work? Yeah, good. Okay, so what we're going to do is that since this is not an easily rounded number, okay, we only round if it's really, really, really close to a whole number. This is not. Okay, this is split in the middle. So what we need to do is multiply this 2.5 times something to get it to a whole number. So what's the simplest one to do then?
2.
Times 2. So we take this times 2. That gives us a 5 for the oxygen. Whatever we do for the oxygen, we then have to do for phosphorus as well. So we take that times 2. Which equals P2. So that's going to mean that our empirical formula is P2O5. So now we're going to move on to our very, very last section called molecular formulas. Okay? What is the empirical formula?
It's the simplest, smallest.
Yeah, exactly. The empirical formula is the very simplest, the most reduced version of a chemical formula. Okay? A molecular formula is the actual chemical formula of a compound. Okay, so the empirical formula was the very, very reduced, like bare bones version. The chemical formula could be the H4O2 or the H6O3 or whatever that bigger version of the 2-to-1 ratio would be. Okay, so these would be molecular formulas. These are not empirical formulas. Okay, the empirical formula of these two is H2O. Okay, the smallest whole number ratio. So we're now going to decipher between empirical formulas and molecular formulas. And we're going to learn how to build a molecular formula.
Oh, wait. So this was like not simplifying?
Kind of. We're going to see how to expand them a little bit. Okay, so let's look at our chemical formula we just found a couple problems ago with phosphorus and oxygen. Okay, we determined that our empirical formula was P2O5. Okay, does everyone remember this problem? We just did it about 10 minutes ago, so hopefully you remember it. Okay, so let's say that we know we're working with this empirical formula. Okay, and they found this is sample problem on page 248 if you want to look at it. Okay, it says empirical formula was found to be P2O5. Experimentation shows that the molar mass of this particular compound is 283.89. 283.89 grams per mole. Okay, so they've found this compound. They know its empirical formula is this, yet they know their molar mass is this. Okay, so we want to check to determine the molecular formula of this compound. So what we do first is we calculate molar mass of our empirical formula to check to make sure if they're the same, okay? Because sometimes it could be the same. So we're going to check to find molar mass of this diphosphorus pentoxide empirical formula, right? That's what the name of it is. Okay, so go ahead and find that molar mass. Okay, so did you get the same molar mass? What did you get, Isaac? Okay, tell me the molar mass first. Of the P2O5. What'd you say? 140 something, not very specific. 142?
I had 141.96.
Okay, that's fine. 142 gram per mole. Okay, so we know that now the molecular formula and the empirical formula are not the same. Okay, we know that these two don't match. So what we do now is we take our molecular molar mass, which is right here. That's of our actual compound, not our reduced compound, our actual compound. We take this molar mass of the molecular formula and we divide it by the empirical molar mass. So we take 283.89 divided by 142, and we see what the ratio would be, or we see what the difference would be. It's 2, right? Did you get about 2? Okay, so that means that the molecular formula, or the actual compound that we're looking at, thank you, is twice as heavy as the empirical formula. It weighs 2 times as much as the empirical formula. Okay, so what we do then, can I clear this screen?
Yes.
Okay, what we do then is if we know it weighs 2 times the empirical formula, we say 2 times P2O5, and we just distribute that 2. So then it becomes P4O10. Okay? And if you would calculate molar mass of this molecule, you should get about 283.89. So let's try one that says, determine a molecular formula of a compound with an empirical formula of CH and a molecular molar mass of 78.11. Okay, so our first step here is to find molar mass of our empirical formula. All right, Hannah, what'd you get for empirical formula molar mass? 13. Okay, because carbon is 12, hydrogen is 1. So that's our molar mass of CH. Okay, so then we take our molecular formula molar mass, we divide it by our empirical formula molar mass. So we take 78.11 divided by 13. And what'd you get? 6. So that means our molecular formula, or our real actual compound that we're looking at, is 6 times as heavy as our empirical formula. So we take our 6 times our empirical formula, and we get C6H6. So C6H6 is the actual formula they're looking at. CH is just the empirical. It's the bare bones. It's the lowest simple whole number ratio of those two elements. Okay?